In this video, I want to use some concepts from complex calculus to show you some important properties of one specific function, which is very important in signal processing, for example, but not just that. And we will focus on the mathematics here, so we will not see any application to signal processing or something like that. But just be aware of the fact that what we are going to see is actually very important, not just in mathematics. And we are going to study the following function, and it's the sinc function, sinc of x, and this function is defined as the sine of x divided by x. Some other times you have a factor of pi, so instead of this definition, you might have the following one. So you have sine of pi x over pi x. But we are going to use the definition, this definition here. So sine of x over x. One of the important properties of this function is that the convolution of this function with itself, with a different argument, so for example, we take sinc of ax, and we take the convolution, and let me also explain what this convolution is in mathematical terms, but we take the convolution with the bx, so we indicate the convolution with this star operator. This basically means that we are going to integrate from minus infinity to plus infinity of sinc of ax minus x0, and then we multiply this with sinc of b x0, we integrate over dx0. Okay, it's basically this. So the convolution is a very important operator, especially when you consider signal processing and the Fourier transform, because it appears in the theory of signal processing, and the Fourier transform of the convolution is very simple. So it is particularly simple to study the convolution when you have Fourier transforms, because the Fourier transform of the convolution is simply equal to the products of the Fourier transforms of the functions here in the integrand that we are multiplying together. So we would have to take the Fourier transform of this sinc function, the Fourier transform of this sinc function, and then we multiply them together. That would be the Fourier transform of the convolution. But I'm just throwing some concepts at you without digging deeper. And in this case, I want to focus not just on, not particularly on the Fourier transform, but I want to focus on this convolution here. And we will prove that the convolution between two sinc functions is still equal to a sinc function, or I should say proportional to a sinc function. We will start from this integral here, and we will carry out the integration. We will resort to complex calculus, as you will see, and we'll prove that this integral here will give us another sinc function. Let me rewrite the integral like this. So we have integral from minus infinity to plus infinity of the sine of a x minus x0 divided by a times x minus x0, and then we have to multiply this with the sine of b x0, we divide by b x0, we integrate over dx0. So we will carry out the integration directly, but I also want to highlight the fact that it would be possible, of course, to prove the same result with the Fourier analysis. And in this case, I will not, let's say, dig deeper. I will not delve into the technicalities of Fourier analysis, because this video will be part of the course on complex calculus, and I didn't delve into the details of Fourier analysis. But I would like to discuss that as well. So if you are interested, you might check out this video, because I want to give you some insights and not just mathematical formulas. Anyway, let's move on. What I want to do next is I want to use a trigonometric identity, a simple trigonometric formula. The formula is the following. So we have the sine of y times the sine of z. It's easy to see that this is equal to 1 over 2 and then I have the cosine of y minus z, and then I have minus the cosine of y plus z. So you can check out that this formula actually holds, and we are going to use this formula here because we have a product of two signs, and we can convert the product of two signs into a difference of cosines. So we have a product of sinusoidal functions. Let's use this identity and replace the identity here in the integrand. So we have integral from minus infinity to plus infinity. Then you have a factor of 1/2, which you can factor out of the integral. You have the cosine of ax minus b plus a x0, and then we divide it by a times b, and then we get x minus x0 times x0, and then we have a minus cosine of ax plus b minus a x0, and we divide it by ab x minus x0 x0. We have to integrate this over dx0. Now, the formula that we have used is particularly convenient because we have written a somewhat complicated integral, and we have let's say we have split it into two different integrals. So we can rewrite this as a difference of integrals. So we have 1 over 2ab integral from minus infinity to plus infinity of the cosine of ax minus b plus a x0 divided by x0 x minus x0 dx0, and then we have minus 1 over 2ab integral from minus infinity to plus infinity of the cosine of ax plus b minus a x0, and we divide it by x0 times x minus x0 dx0. At this point, we are going to do two different substitutions. The first substitution is for this integral here, so we are going to replace the argument of this cosine with another variable that we will call t. So we will set t equal to this argument here. That's ax minus b plus a x0. From this you can derive x0 equal to ax minus t divided by b plus a, and also you can calculate x minus x0 by using this definition for x0, and you can easily check that this is equal to bx plus t divided by b plus a. And you do something similar for the second integral. In this case, we are going to use the variable w, and we set it equal to the argument of the cosine of the second integral. So here I set it equal to ax plus b minus a times x0. From here you can derive x0 equal to w minus ax divided by b minus a, and then you can also derive x minus x0, which is equal to bx minus w divided by b minus a. So it's easy to check. This expression holds from this one. And now you can do this substitution, and in doing the substitution we will assume that a is greater than b. So in evaluating this integral here, this is the convolution, we will assume that a is greater than b. Of course, you can derive also very similar results if you set b greater than a. It doesn't really matter. We have made a choice, In this convolution here, we know that a and b are real numbers, and for simplicity we can think of them as positive numbers, and then we just choose one of them to be greater than the other. And by the way, this integral here with this convolution is also the same if you, instead of writing x minus x0 here and x0 here, well, you can put x minus x0 here and also here, and instead of x minus x0 here you can put x0 and also here. So the convolution has this of course symmetric property, and it's very easy to verify. Anyway, we take this as the starting point. We use also some trigonometry and we derive this formula here. Now we make these two substitutions, and from here we derive the following. So this is equal to, we have 1 over 2ba, or ab, whatever you want to write it, and then we have integral, and now here I have plus infinity to minus infinity, because if you check from here, well, if you set t equal to minus infinity, sorry, actually we have to start from x0. So if x0 starts at minus infinity here, you see that with this minus sign, the minus infinity will become a plus infinity. So here that's why we have plus infinity, because b and a are both positive. And of course, here you will have minus infinity when x0 is equal to plus infinity. T will go to minus infinity due to this minus sign. So here you have the cosine of t divided by, and then here you replace these two. So you have ax minus t divided by b plus a, and then you have bx plus t divided by b plus a, and then here you have minus dt divided by b plus a. Then you have minus 1 over 2ab integral. This integral here will start at plus infinity and it will go to minus infinity. We start at plus infinity here because we have chosen a greater than b, so b minus a will be negative, and it means that when x0 tends to minus infinity, since this is negative, w will tend to plus infinity. And similarly for minus infinity here. Then you have cosine of w, you divide by w minus ax divided by b minus a, then you have bx minus w divided by b minus a, and then here you have dw divided by b minus a, like this. Now one more step, one more rearrangement. So this is equal to, we can rewrite it as b plus a divided by 2ba. Then we have integral from minus infinity to plus infinity. So I have swapped the order of integration. So we start at minus infinity and we go to plus infinity. So I have to change the sign. So this minus will turn into a plus. And then I have cosine of t. We divide by ax minus t. And then we have bx plus t. We have dt. And then here we have plus. So this minus, I will turn it into a plus by swapping the order of these two integration limits. So we have b minus a divided by 2ab, integral from minus infinity to plus infinity, cosine of w divided by ax minus w. Then we have minus bx plus w dw. So I have also changed the sign here and also here. So the product of these two together is equal to the product of these two, with a change in sign in both of them. So you can check easily that this equation here, I mean this integral, can be written like this, in this form as well. And now we can resort to complex calculus. And I will leave this as an exercise for you. In particular, you can calculate this integral here with complex calculus, and you can check actually that you can write it in the same form as this one on the right. So when you calculate the one on the left, well, you know how to calculate also the one on the right. You can write some expression and evaluate the complex, the complex integral by using residues. You turn this into a complex integral. You calculate the integral by using the residue theorem, and it is possible to attribute a value to this integral here and also to this integral here by means of the residue theorem. In this case, I will leave this as an exercise for you. I don't know, maybe in one of the following lectures, I might also give you a solution, or I will give you more hints as to how to calculate this integral here, these integrals. And in this case, I will give you the result, so you can check that this integral on the left is equal to the real part of I pi divided by x, a plus b here in the denominator, and then we have e to the minus I bx minus e to the I ax, whereas this integral on the right is equal to the real part of I pi divided by x times a minus b, and then you have e to the I bx, and then you have minus e to the I ax. And you can put these results together. So you just simply substitute the expressions here and here. And in this case, let me just skip the algebra. With very simple steps, you can get to the solution. And the solution is equal to pi over a, and then you have the sine of bx divided by bx. So you can see that the result is still proportional to the sinc function, because this is sinc of bx. You can see there is this scaling factor. We divide by a, and we also have this constant pi. And let me give you some more hints into, let's say, why this result is true, is correct, by telling you a bit more about the Fourier transform properties. In this case, I just want to give you a hint. If you don't know much about Fourier transforms, you might as well skip this part. But it might be interesting. So that's why I want to give some more information to you. And if you're interested, well, feel free to check the following part of this lecture. Now, let me define the Fourier transform, and in particular, the Fourier transform of a function. It can be defined like this. So we integrate from minus infinity to plus infinity. Here we have the function. In this case, as a function, we take the sinc function. So let me write the sine of t divided by t. So we start from the time variable, and this is sinc of t, if you want. And then we multiply this by the complex exponential e to the minus I omega t dt. So it is also possible to evaluate this integral by means of the residue theorem, if you think about it. So it is not complicated to evaluate this integral by means of residues, if you want. In this case, I would just want to give you the result. This integral evaluates to pi times the rectangular function that I will define shortly of omega. So in particular, pi times the rectangular function of omega will give you the following plot. The rectangular function, you can easily guess that it will be indeed something rectangular, so it will be a constant inside some domain, and it will be 0 outside of that domain. So in particular, here we have on the x-axis we have omega, and this function is defined as a constant between -1 and 1. So outside of this region, the function will take a value 0. And then the height of the function is just equal to pi. And it is due to this pi here, because if pi were not here, this would be equal to 1, this height. Simple as that. Then we can evaluate the Fourier transform also of the sinc function of at. So sinc of at. We can integrate this from minus infinity to plus infinity. We have to multiply this by the usual complex exponential of the Fourier transform, which is e to the minus I omega t dt. And, well, you can rewrite this as integral from minus infinity to plus infinity of the sine of at divided by at. And then you can write e to the minus I. We divide omega by a and we multiply it by at. Then we take the differential of at and we divide by a. So I have simply rewritten the formula in a different manner to show you that with the simple change of variable, you can see that this is equal to pi, the rectangular function of omega divided by a, and then we divide by a. So if you plot this is equal to the following plot. Let me make a sketch, a simple sketch. The plot goes from minus a to a, and inside this region it is just a constant. The height of this function is equal to pi divided by a, and that's basically it, right? So this is the rectangular function multiplied by pi over a. And similarly, you can take the Fourier transform of the sinc function of bt. So if you take the Fourier transform of this, let me denote it like this, you will get pi times the rectangular function of omega over b divided by b. So you get exactly the same plot, but instead of a, you will have b, right? Now, since a is greater than b, if you multiply this function here with this function here, so we are multiplying basically the Fourier transforms of the sinc function. So we multiply the Fourier transform of sinc of at with the Fourier transform of sinc of bt. So this is equal to, we get pi squared rectangular function of omega over b divided by b, and then we get rectangular function of omega over a divided by a. And remember the plots for these rectangular functions. Since we assumed that a is greater than b, when we make the multiplication between rectangular of omega over b and rectangular of omega over a will simply give you this product here, will give you rectangular function of omega over b, if you think about it, because a is greater than b, right? And the height of the rectangular function is just equal to 1 by definition. So rectangular of omega over b is like this, where the height is equal to 1. We go from minus b to b, like this. And also, if you plot the rectangular function of omega over a, since a is greater than b, you will have something like this. So you go from minus a to a, like this. And when you multiply them together, you simply get this, because this function is equal to 0. Here, 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 here. So you're just going to get back the rectangular function of omega over b. Basically, this will give you pi squared divided by b, or actually let's put a here, and then we get rectangular of omega over b divided by b. And remember that, well, this function here, or actually, let me go back here. So you can see that pi over b times the rectangular of omega over b is equal to the Fourier transform of the sinc of bt. So this is equal to pi over a, let me write it like this. So this is the Fourier transform of pi over a, and then we get sinc of bt. But remember where we started. We started from the product of these Fourier transforms. If we take the inverse Fourier transform of this, we know, according to the properties of the Fourier transform, that since we are taking the inverse Fourier transform of the product of these Fourier transforms, in the time domain we are going to get the convolution. So let's just denote it like this. The convolution between sinc of AT with the sinc of BT. And when we take the inverse Fourier transform of this, we're just going to get this argument. So we just get that this is equal to pi over a sinc of bt, which is exactly what we expected because it's what we derived in a direct manner. Here, where we, in this case, we just called the variable was x, right? So in this case, we used x as the variable, but basically, it is just a result that you can derive in multiple ways by using either the Fourier transform or just with the straight calculation by using the convolution integral.